day, everyone. I am Alain Vianica Paharillo Yabut of BFEE 2A, and today I am going to discuss the expected values of functions of random variables under multivariate probability distributions. When we encounter problems that involve more than one random variable, we often combine the variables into a single function. We might be interested in the average life length of five different electronic components within the same system, or the difference between two different strength test measurements on the same section of cable. We now discuss how to find expected values of functions of more than one random variable. The basic procedure for finding expected values in the bivariate case is given below. It can be generalized to higher dimensions. Suppose the discrete random variables x sub 1, x sub 2 have a joint probability function given by p of x sub 1, x sub 2. If g of x sub 1, x sub 2 is any real valued function of x sub 1, x sub 2, then the formula is written in the box below. The sum is over all values of x sub 1, x sub 2 for which p of x sub 1, x sub 2 is greater than 0. If x sub 1, x sub 2 are continuous random variables with probability density function f of x sub 1, x sub 2, then the formula is also written in the box below. It could also be written similar to the formula in the red box. A function of two variables that is commonly of interest in probabilistic and statistical problems is the covariance. The covariance between two random variables x sub 1 and x sub 2 is given by the formula below, where mu sub 1 or mean sub 1 is equal to x of x sub 1 and mu or mean sub 2 is equal to e of x sub 2. The covariance helps us assess the relationship between two variables in the following sense. If x sub 2 tends to be large when x sub 1 is large and small when x sub 1 is small, then x sub 1 and x sub 2 will have a positive covariance. If, on the other hand, x sub 2 tends to be small when x sub 1 is large and large when x sub 1 is small, then the variables will have a negative covariance. Whereas covariance measures the direction of the association between two random variables, correlation measures the strength of the association. The correlation between two random variables x sub 1 and x sub 2 is given by the formula in the box. The correlation coefficient is a unitless quantity taking on values between -1 and +1. If ρ is equal to +1 or ρ is equal to -1, then x sub 2 must be a linear function of x sub 1. A simpler computational form for the covariance is given below without proof. If x sub 1 has a mean mu sub 1 and x sub 2 has a mean mu sub 2, then covariance of x sub 1 and x sub 2 is equal to e of x sub 1, x sub 2 minus mu sub 1, mu sub 2. If x sub 1 and x sub 2 are independent random variables, then e of x sub 1, x sub 2 is equal to e of x sub 1 multiplied by e of x sub 2. From the computational form of covariance, it is clear that independence between x sub 1 and x sub 2 implies that covariance x sub 1, x sub 2 is equal to 0. The converse is not necessarily true. That is, zero covariance does not imply that the variables are independent. To see this, look at the joint distribution in the table. As for example number 1, a firm that sells word processing systems keeps track of the number of customers who call on any one day and the number of orders placed on any one day. Let x sub 1 denote the number of calls, x sub 2 the number of orders placed, and p of x sub 1, x sub 2 the joint probability function for x sub 1, x sub 2. Records indicate that p of 00 is equal to 0.04, p of 10 is equal to 0.16, p of 11 is equal to 0.10, p of 20 is equal to 0.20, p of 21 is equal to 0.30, and p of 22 is equal to 0.20. That is, for any given day, the probability of, say, 2 calls and 1 orders is 0.30. Find covariance of x sub 1, x sub 2. And the solution would be When a problem involves n random variables, x sub 1, x sub 2 to x sub n, we are often interested in studying linear combinations of those variables. For example, if the random variables measure the quarterly incomes for n plants in a corporation, we might want to look at their sum or average. If x sub 1 represents the monthly cost of servicing defective plants before a new quality control system was installed, and x sub 2 denotes that cost after the system was placed in operation, then we might want to study x sub 1 minus x sub 2. A general result for the mean and variance of a linear combination of random variables is given below. To further widen our knowledge on how to find expected values of functions of random variables, let's take a look at this another example. And that's all for expected values of functions of random variables under multivariate probability distribution. I hope you learned something from me and thank you for watching. Goodbye!